Hello, everyone. My name is Quan-Chen Wu, and I'm an instructor for the InSpirit AI program. And I'm happy to give you a brief introduction to computer vision and neural networks. But we have a time limit. So my presentation will just take the next 20 minutes, and then I'll offer a Q&A for the last 10 minutes. So we're going to go pretty fast. But if you keyboard warriors out there are fast enough, when I ask questions and you type it into the chat and you're one of the first, I will call out your answers for everyone to hear it. Okay, so let's get started. We want to help computers see using deep learning. Now, what I'm doing is I'm just giving you an excerpt from a fuller lecture. So this is going to be a mini lecture. It's going to be fast paced, but if I skip some slides, don't be too worried about that. I just want to give you, for those of you who haven't seen a computer vision much before, this will be hopefully exciting. And then if you have seen computer vision, I hope to add to your knowledge. Okay. So with computer vision, we have to deal with images, which constitute video. And then we also want to use neural networks to help us. And then that involves some training process. And we'll skip the math for this short time period. Computer vision is used in many places, including self-driving cars. Clearly, Tesla, has videos of their product, autopilot, and so here's their demo. And we don't need this sound, but just give you a taste of all the different channels of information that they process. This is just visual and some, from multiple angles. There are supplementary channels of information as well, such as LiDAR, radar, and other technologies. But clearly one of the main components is camera-based computer vision. So the question we have is, how do we go from this image on the left into this processed or refined image on the right, where the vision algorithm has identified certain key objects of interest? Okay, so you see here the road sign, the lane lines, the boundary markers. Okay, so that's what we're going to talk about. Now, when you and I look at a stop sign, we see a concept, something meaningful. But the computer also needs to develop some intuition behind that, and it doesn't have a clue at the beginning. So what we want to do is to help it to develop that meaning, and that's through a training process. Just to recap, AI is used for computer vision in order to help computers train and interpret and understand the visual world. Some other examples of computer vision here, you see like a hand sanitizer station. This system just monitors how people are using the hand sanitizer station, and then possibly give some recommendations. For example, it could measure the time between when a person's hand is underneath the dispenser, and then it can recommend perhaps, hey, it's too short, maybe you want to use it a little bit longer. Okay. So at this point, what other examples of computer vision can you put into the chat? Okay. Just waiting for one or two responses. Okay, facial recognition and Google Lens, excellent examples. And so here we'll get to see a little bit of how that might be possible. Also, Snapchat filters is an instance of this. And so the tasks here that the filter has to perform for the computer is it has to detect a face. So that recognition is a task in itself. And then once it has a face, a human face, then it tries to identify landmarks. such as anchor points, reference points, the eyes, the center of the pupils, the corners of the mouth, the eyebrow location, the nose center, etc. And then the third step is to process by adding some graphics or manipulations. So you see that illustrated in the bottom sequence of images here. But in order to do that, we need to convert from images to numbers because computers process crunch the numbers. So this cute little dog here, we need to express that image as numbers. And this is just a basic introduction to digital representations and file formats. Well, an image is able to be thought of as just a matrix of numbers. So you see the pixelation here in the middle. And one instance of this is suppose we have the letter S or that portion from the dog's ear. And you can convert it on a grayscale, if it's a grayscale image, to a matrix of numbers, grayscale values, okay, where where 0 represents one extreme, and in this case, if it's 8-bit, 256, max value 255, that could be the other extreme. Okay, now whether 0 represents white or black depends on your particular choice. Okay, so people do it for different reasons, one way or another. And so the intensity of the pixel is represented by the matrix value. And in this case, 0 is black, 255 is lightest, and that's pretty common. And so there is an S shape hidden in here where the S shape is dark. So if anyone is able to annotate, you can mark the S. So go ahead and try that if you have Zoom available, if you're savvy on that. But I'm going to just start because of our time. So I'm going to start right around here. And I'm going to go like right around here. And maybe I'm not doing such a good job, okay? But it should be like around here, okay? And so that's the exercise here. But here we want, actually we want we want to go from darkest, which is values near 0. Okay, so you see this type of shape. Okay. You trace out the low values. All right, and so let's move on here, and let me clear out the drawings. Okay, so computers, the computer vision will operate on all these matrices of numbers, and that's what we need to proceed, okay, to develop. Now, that was just grayscale or black and white images. What about a color image? So, yeah, exactly. TO, RGB, yeah, that's one system. There's also other systems like HSV and hex. Yeah, the numbers are often represented as hex, hexadecimals, but the interpretation is dealing with at least 3 degrees of freedom, 3 channels of information. There's also RBG, which is used in OpenCV, as you'll find out when you progress on programming this. So we've just established the color images can be thought of as 3D arrays. For example, our red channel, green matrix, and blue matrix. Okay, so when you stack them up like this, you can consider it a tensor, but you can also think of it as just 3 layers of matrices. A little bit about color. So would anyone like to annotate or put into chat what you think yellow, white, and black are, and then gray as well? So if you're feeling ambitious, you can try gray. Okay, so if we're using max 255, what would be some integer values for yellow? Okay, 255, 255, 0 black. Yep, teal, got it. White, yep. Treasure hacks, yep. Okay, yellow, 255, 255, 0. Yeah, because that one's actually a little bit tricky. Okay, so great. Someone got the gray. Exactly. When all three values are equal, you get like a flat gray. And then whether it's 128, 128, 128, or 250, 250, 250, that just changes the shade of the gray. Excellent, excellent. Just keep in mind though that there for this color scheme, it's actually so there's additive and subtractive light models, but we don't need to get into that right now. But just keep in mind the color wheel, when you mix colors on paint or pigments, that's different from the colors when you talk about a computer screen. Okay, but this is all further details that you can dig into. And so now we talk about matrices. What about the size? How much memory do you need? Okay, so how many intensity values are there in 1,000 by 1,000 RGB image? So first person to enter that into the chat. Okay, you're not accounting for the three channels. Okay, it's 1,000 by 1,000, by the way. So that product is at least 1 million, right? Yeah, okay, good. 3 million, that's right. Now that's how many values we need to fill in order to define this image, okay? Good. Now, so that's a little bit of basics on image. Now we're getting to the fun stuff about neural networks. So neural networks are a way to deep learn image processing. So if you try to explain or differentiate, how would you tell the difference between this cat and this dog? Heuristically. So we're talking here about heuristics or rule-based. So just try a couple of rules that you might differentiate one from the other. Yeah, their faces look different. They have different proportions. You might hear some people talk about Euclidean distances or manifold distances on the curved surfaces. Ears, yeah, their ears look different. In this case, it happens to be flapping down, but something like a German Shepherd's ears would also look pointy. So good responses here. The point is, no matter how many features how many rules for differentiating between these two animals you come up with, it's going to have weaknesses, right? It's going to have counterexamples, so it's going to fail. That's why we want neural networks to learn the features. We don't want to predefine features like we're trying to do here. And so the deep learning avoids the predefinition of features, and we let the neural network learn its own understanding of features from the data that it is fed, okay, that we feed to it. So you may have heard of classification algorithms like logistic regression, which can be used for classification, but they don't work well for computer vision. That's why we need neural networks. And one of the key insights as to why other machine learning algorithms that are not suited for vision don't work so well for vision is because they don't take advantage of the fact that in an image, the pixels location relative to one another has meaning. For example, just as a simple analogy, on a human face, you usually have two eyes, and you usually have a nose somewhere somewhere beneath them if the image is right side up, and you have a mouth somewhere, and you have some like eyebrows. So the fact that these two pixels right next to each other on my forehead are not randomly placed. Right, there's some order to them. There's some hierarchy. So that's what neural networks take advantage of when they process images. Okay, and yeah, so they can recognize complex patterns. And at this point, I'm going to just show you when you learn about there's this whole sequence. You learn about neural networks, and then you talk about the multi-layer perceptron as the starting point, and then you cover convolutional neural networks, And then you can combine the neural network architectures creatively. There's so much room. One of the exciting things about AI is there's so much room for novelty, for inventing new things, that you can create neural networks from other neural networks, kind of like Lego blocks. You know, you build Legos into certain subunits, and then you can put those together for a larger object. Okay, and neural networks are the same. And historically there was an image image recognition network called AlexNet, and then there's also like DarkNet. But then along comes this YOLO framework, and it stands for you only look once. And it's a way to, I'm kind of jumping forward ahead because, you know, there's a lot of knowledge in between. But if we skip to something cool like this YOLO, it's an end-to-end. It's designed for speed, so almost real time. So YOLO, at least version 3, can go up to like 45 to 60 frames per second of processing. That's almost real time on reasonable hardware. Okay. And then there are other subsequent improvements such as YOLO v4, YOLO v5. It's, you know, they try to increase the speed and accuracy. But here, what YOLO does is it follows a multi-scaling approach in order to quickly identify bounding boxes and then to recognize the objects inside. It, by default, can recognize, is pre-trained to recognize 80 classes, okay, in most implementations. You might find some variations on that, but basically if it's one of the 80 things that it knows how to detect, it can detect it quite rapidly. And then, yeah, so there's an additional detail. It will detect a lot of different candidates for one object, but then it will go through a pruning process to shrink it to identify the most likely bounding box, the most accurate bounding box for your object. So here is one of my students' YOLO outputs from just last night. They shared it, and so I thought I would share it with you. This is real, his own cell phone highway footage, and so you can see that he's just riding down the highway, and it will pick up cars and trucks. But there are, 78 other categories of, for example, people, traffic lights that can be detected. So YOLO is just one cool application of computer vision. And if we were to, go into a more complete lecture, there's a lot of additional topics that we would go over. For example, the biological inspiration behind neural networks. They mimic the way human neurons and synapses operate. And then we would talk about the math, and then we talk about the topology, okay, and then various hyperparameters. But for now, I hope this is just one way to spark your interest in computer vision, and I'm welcoming your questions for the remaining time. Thank you. And you can ask your questions in chat, or if you would like to unmute and just ask me directly, that'd be fine too. Also, if you've been introduced to this material, let me know as well, and ask me some more advanced questions. And also feel free to turn your camera on if you would like to ask, because I'd like to meet people. Okay, in many cases, object distance, this is in the chat, is also very important. So how is that calculated here? Yeah, yeah, in this case, we're not estimating the real life sizes of the objects we're detecting. We're just recognizing them. So the convolutional neural net will take care of the automatic scaling because when it reduces, it will take care of the object scaling as a part of its training? It's a good question. So we don't explicitly calculate the real world object estimates here as part of YOLO, but you can do that, especially for self-driving cars. They will have some kind of relation, for example, a LiDAR measurement. You need to know the distance, right? And then you can perform a mapping, a translation of scaling into real world coordinates versus the recognition space coordinates. Great. Any other questions? Does that answer the question sufficiently? I mean, there's a lot more that we can get into on that question. Okay. All right, we have a couple more minutes.
If I might ask a question, I've been researching into machine learning and AI as well, but I was wondering what would be good places to search for resources to learn about, because of linear regression, gradient descent, neural networks, split into like, would it be high level machine learning and low level machine learning? Because neural networks are more high level, gradient descent, linear regression more low level.
Yeah, you can.
Sorry. But literally what I've been doing is just reading Wikipedia, but I was wondering if there's a better place to find like free resources to explore these concepts.
Excellent question. Yeah, we all to some extent can traverse Wikipedia, link to link, and kind of get lost in the sea of information there. There are two there. So the breakdown that you suggested is one way to do it, like neural network high level, gradient descent as low level. I would think of it also as application versus a fundamental, a theory. So the theory, you need to have some back. If you really want to understand, so there's one. If you want a shallow, you just want a quick introduction and get something done, a project done in computer vision, you can do that by just applying some tutorials, and there are packages that will speed you along, and YouTube videos, and other types of videos. But if you really want to understand the theory of why it works and what it's doing and how to make it better, you really need to dig down into the math. Okay, so the theory, so the quantitative side. And I didn't have time to get into some of the math behind the neural networks, but I think that's an important way to, if you really want to go far in the field of AI. You really need to get so that you can't really accelerate. You need to do a complete calculus sequence. You need to do some optimization theory, statistics, probability. Some graph theory, perhaps. So, as much math as you can. I don't think you can do too much math if you want to excel in AI. Mm-hmm. There's a quote that I could share. You can be a very good data scientist or artificial intelligence practitioner without deep math, but you cannot be a truly great AI researcher or computer vision expert without deep math. So that takes time. But in the short term, you mentioned some free resources. Yeah, there are plenty of tutorial videos that you can find online, and additional courses. So with InSpirit, we give the students both some theory, enough theory so that they feel comfortable what's going on behind the scenes, and then also some practical, get them on a project, and then help them to build something like this. So it really helps your learning when you get that practical aspect.
Sounds good. Thank you.
Great. Okay. Also, another question: what's the process of training to neural network to recognize new objects from what this student has seen? There's usually a data set that has been interpreted manually that it learns from, but are there other more efficient methods? Yeah, that's a key point there. The data, the availability of high quality, correct labeled data is a challenge. It's a challenge that never ends. All the companies are struggling with that. And so there are other companies formed to provide, supervised labeled data sources. But then you may also have to hire, other people to train it. You may have other AI that's specifically intended to train other AI. Okay, so it's a whole ecosystem of AI machine learning models that can be triggered to teach each other, similar to how humans can interact with each other. But yes, the original this YOLO example, I think it was we used the darknet, right? It's the YOLO v3. The base implementation is based on darknet, and darknet was trained on labeled data. And so there are a number of large data sets which are available open source or semi open source on the internet. So one of those is called ImageNet. And another one is COCO, CIFAR, CIFAR. So you can find these. Also, Kaggle has some data sets that are available, and many other sources. So nowadays, again, part of the excitement, enthusiasm for data science and AI is there's more and more data available that people want you to, run on, right? And whether, climate studies, epidemiology data sets. And so that's where you can apply all of your creativity and talent to try to help make the world a better place through AI. Okay, so we are nearing the end of our time together. You're welcome. And so any last minute questions? There's so much to learn and play with in this field. So I hope that today's seminar, brief workshop, will help you along and stimulate your interest. Okay, thank you, Brandon.
Thank you so much also just for taking your time and doing this. And if there's no other questions, let's end the stream here for YouTube. And if anything else is here, I guess we'll catch it. So yeah, thank you so much.
Yeah, thank you so much.